Hello, good afternoon, everybody. All right, welcome back. And today we will talk about the advanced version or enhanced version for Dfs Forest search. We will first have some review about the previous contents. We actually compare the Dfs two versions of the DFS, right? We have first the recursive version, which is a simple recursive procedure that calls itself, right? So it basically it starts with the source vertex, right? It will set the visited variable, the visited attribute to true, and then go through all the adjacent vertices in the adjacent list, right? And for each visit, it will call the function, call itself recursively. All right. And the non-recursive, the iterative version for DFS uses a stack data structure. Okay. So it will, like, whenever it has met a vertex, it will push the vertex into the stack, right? And while the stack is not empty, it will keep popping out vertices. And if that vertex is not visited, then it will go through the adjacency list for that vertex and push that vertex to the stack, right? So these two versions for DFS, we call it simplified, simpler versions for DFS, because we don't record extra information like the parents child relationship, right? The descendant versus ancestor relationship was not recorded, was not saved in either versions for DFS. But in practice, we will need to have such information because DFS is sometimes not the end of the algorithm. It is just a pre-processing of a graph. And the structural information returned by the DFS can then be used in some more advanced algorithms, or some algorithms that are for specific questions. Okay, so we will need more information than this. So that's why we will introduce the enhanced version for DFS first, for DFS today. So before we started, I think we didn't cover these slides in the last lecture, right? So because in the example that we have for the simple examples, for the simple graph, we actually can, the DFS will result in a DFS tree, right? Which basically connects all the vertices in the graph. Okay, and that is the ideal case because sometimes the vertices, not all the vertices in the graph are actually connected or reachable from each other, right? So in those cases, we will not have trees, but rather we will have multiple trees. Okay, so in case that some vertices in the graph may not be reachable from the source that we choose, so we can use by deliberatively introduce some for loops. For example, in this case, we will use a for loop, right, to go through all the vertices in that graph, so that we make sure that each vertex has been visited, right? And during each visit, we will call either the DFS recursive or the DFS iterative to start from that vertex as the source. Okay, so if we take such a way, use a for loop to go through all the vertices, then basically all the vertices will be covered, right? And if some vertices are not reachable from the source, then the DFS will basically, the DFS procedure will return a collection of forest, okay, or a set of a collection of trees. So you can call it a Dfs forest, right? A forest is a collection or a set of trees. Okay, so for instance, if we still use the same graph, right, and we will call the DFS on this graph and assume that we will start from the vertex W, right? Okay, so the thing with the graph, the directional graph, is that although the vertex U has an edge from U to W, right, but it's directional, right, and the connection from U to V is also directional, right? So it looks like if we start our search from the vertex W, if we follow the DFS principle, right, we go from W to X, and then probably X to Y, right? And then X to V, right? So that'll give us the first tree, right? It's basically in such a shape. And the second, according to the for loop, right, we need to go through all the vertices in the graph. So it then can, the next iteration for the for loop could be X or Y or V, right? But in these three cases, since X, Y, and V are already visited during the DFS from W, so there will be no more DFS recursive or DFS iterative called. So the for loop will proceed on to the vertex U, okay? But now since the vertex U, right, it's basically isolated from the other vertices, because we cannot reach W, X, V, or Y to that U. So the U alone will be a single DFS tree, okay? So which only has U as the root node, right? So that's why we will have two components or two trees in the Dfs forest, right? So in theory, this principle, like this method, use a for loop to go through all the vertices, not just apply to Dfs, but also to BFS, right? To breadth first search. But in the example that we gave last week, we didn't use this for loop to wrap around the BFS algorithm, because we just hold a simple assumption that all the nodes are reachable from the source, right? But it's a very flexible strategy. Like if you want to make sure that all the vertices will be visited, then you basically want to have such a for loop. Okay. All right. So that will be some of the basis for our discussion on the enhanced version for DFS today. Yeah, let me quit sharing and start playing the slides. Okay, share it again. All right. This will be the enhanced version for DFS, right? All right, so this procedure will not only colors vertices during the search, right? Because we know in the BFS, we know that the search procedure can use 3 colors, right? It can assume that all the vertices starts with white, right? And when all the adjacent vertices has been visited, then one vertex can become black, and those vertices in between are somehow paid with gray color, right? So that's the principle for the BFS that we introduced at the beginning. So we can take the same principle here. So this is the coloring is not something new here, right? But the new attributes that we will use is that we will define the concepts of discovering time and finish time, right? So we say a vertex is discovered when it's becoming gray from white, right? So it becomes gray when it is first discovered, okay? And when the adjacency list for that vertex has been completely examined, right? Which means all the adjacency vertices has been visited, then we say that vertex is finished. Okay, that is also the time that it becomes from gray to black. Okay, so there are two critical time steps, which is the discovery time and the finish time, that we want to mark as useful attributes in this algorithm. Okay, all right. So we will use the D and F attributes for the discovery time and finish time for each vertex. Okay, right. So that's V dot D and V dot F. Okay, and of course we would know that it has the D is always smaller than F, because it's never it will never be finished until we start it, right? And also the vertex is always white before its own starting time stamp, right? And it's stays in gray color between the starting time and the finish time. So that is the some simple principles. Okay, so in order to achieve this, so because we want to the result we want to achieve is that after the DFS is done, all the vertices in the graph will be assigned with the dot D and the dot F attributes properly. Okay, so we will, in order to achieve that, we will need to have some global variable to that we define a procedure to keep track of the global timestamp, right? So we will have some variable called time in the procedure, which is shared across all the vertices. Okay, right. So the algorithm will have two components. It's a bit similar to the DFS that we introduced in the previous slide, right? Because if you, right, let's go back again. In the previous slide, we have, right, basically we have a DFS as a wrapper, right, that wraps around the DFS recursive, right? So it will have a for loop to make sure that all the vertices have a chance to be visited. So here we take the same principle that we will have a function, a procedure defined as DFS, right? So first, the for loops here is just for, right, for the correct initialization, right? It will paint all the vertices to white color, right? And the parents attributes will be set to be none, right? And more importantly, we have something known as time. Okay, and this time you can think of it as a global variable that it can be accessed even within this procedure, right? It's declared outside the context of this procedure. Okay, so the time is initialized to 0. Okay, and what's next is similar to the DFS. It's basically a for loop, right? That goes through all the vertices in the graph, right? If that vertex is not visited yet, right, because it's white. If it's still white, then we will call DFS visit. Okay. So the DFS visit here actually plays a similar role to the DFS iterative or DFS recursive, right? Only the difference is that the DFS visit here should achieve these functions. It should calculate the discovery time, the finish time for each vertex, right, by using the time variable here. All right, so here's how the DFS visit looks like. Okay, so let's look at an example, right? So let's first analyze the code a little bit before we enter the example. So the DFS visits, it can also access the global variable time, right? So when in each call of this DFS visit, it will increment the time variable by 1, right? Because it is an effective operation, right? It takes one time step to go from one vertex to visit the other, right? So that is the time necessary for visiting each vertex. Okay, and after that time is incremented, it will be immediately recorded into these attributes, which is the starting time for the vertex u, right? And u is here passed as an argument. Okay, and the color of u also becomes gray, right? Because the if statement makes sure that we will only call DFS when that vertex is the color of that vertex is white, right? So we will need to mark it as visited into a gray color, into the gray color, right? And what's next? This for loop is actually pretty similar to the recursive definition for DFS. Remember, right? So in the recursive DFS, we need to go through all the adjacent vertices for u, which is stored in this adjacency list for you, right? And for each vertex in the adjacency list, we will first check whether the color is white. And if true, we will set the parents for v to be u, right? Because we will need to go from u to v so that v is visited, right? And the DFS will also called recursively on that child vertex v. Okay, so this is a typical recursive implementation, right? And that is after this for loop is done, which means all the adjacent vertices for u is visited. Then the color of u needs to be changed, right? Because when all the adjacency list has been completely examined, then it will become black, right? That is the time step that u has been all the adjacent vertices for u has been visited. So we need to set the color for u to be black, and then increment the time step, the global time again by 1, and mark this time as the finish time for the vertex u. Okay, so you see that within this recursive call, the starting time is changed at the beginning, right? Only after all the adjacency vertices has been visited, the starting time, the finishing time will be set. Okay, so the finish time will always be greater than the starting time. And within this range, within the range between the scope of starting time and the finishing time, the color of U will always be gray, right? Because it will only become black when the time reaches the finishing time. All right, so let's look at how this procedure runs on a specific example. Okay. Yeah, I will paste the algorithm here. And this is the graph that we will go through. It looks it's a pretty simple graph, right? So assume that the vertex U is the vertex that we start from, right? And because remember the time is initially 0, right? In another procedure, in the DFS procedure, we initialize time to be 0. So the first, the starting time, the discovery time for U would be 0 plus 1, which is 1. So we write the starting time here at the left side of the slash, and towards the right, it will be the finish time, right? All right, so U will be the one first discovered, right? So according to the algorithm, we need to paint it to the gray color, and then we need to go through all the adjacency vertices, which is V and X, right? Let's assume that it will go through the vertex V, and that's order or sequence is just arbitrarily chosen, okay? Let's assume that we go to the V, and then because the V is initially white, right? So the parents of V will be set to be U. So the parent relationship between U and V is defined here by this dot pi attribute. So that's why we paint this connection, paint this edge to be a darker into a bold line type, right? We use this bold edge to indicate that this is a parent relationship, okay? And then DFS visits will be called upon this V, okay? So V will be painted from white to gray. And remember, in the first line of the DFS visits, when this DFS visit is called upon V, the global time will become from 1 to 1 plus 1, which is 2, right? It's a global time step. So the discovery time for V would be recorded as 2, okay? And this time we need to go through all the adjacent vertices for V, right? If you look at the adjacency list for V, it will only be, right, Y, right? So we will go through the Y, and the discovery time would be incremented again, which is 3. And then when Y is done, we will need to go to X, right? Because X is also in Y's adjacency list, right? And the starting time for X would be, the discovery time for X would be 4, okay? So now it's, we reached a point that if we look at the adjacency list for X, it will contain the vertex V, right? But since the color of V is already gray, it's no longer white, so there will be no more DFS visits called during the visit for X. So now it will be the time that the color of X will be painted to black, right? Because the for loop is done, and it is a line 8 that needs to be executed, okay? So before that step, here we have a special concept or special notation that you see there's a connection, there's an edge from the vertex X to V, okay? And in the textbook, this edge from X to V is called a back edge, right? It's also labeled as this capital B, right? But since this basically the meaning for the back is that it's connecting from some child vertex to some ancestor vertex, right? Because according to these edges, V is the parent for Y and Y is the parent for X. So relatively speaking, X is the descendant and Y and V is the ancestor. So if a edge is connecting from a descendant to an ancestor, it will be called this back edge, right? But since the algorithm provided in the textbook is not has not implemented this how this edge is labeled, so we will just keep it as some notation here. It will be useful when we analyze the structure of the resulting Dfs Forest, right? Dfs Forest, but we will not look into the details how this is implemented. Okay. All right. So the next step is that we need to mark the finish time for the vertex X, right? Because all the adjacency list for X has been visited. So, right. So in the next slide, we will see that the finish time for the X would be 5, right? Because the time step will the time will be incremented by 1 before it's finished, right? So X is also colored to black. Okay. So the question now becomes, what would be the next step, right? So we need to notice that here. Let's go through the order again, right? We start from U. We mark the discovery time, but we left the finish time like blank, right? And then we go deep to visit the child vertex V, right? And we also mark the discovery time and leave the finish time empty. And then we go to Y with some discovery time and empty, and then go to X with discovery time 4. And now since X has nowhere to go, so we will have to mark the finish time as 5, right? So since X is done, which means we need to now trace back, go back, right? Go back to X parent, since now all the child vertices for Y has been visited. We need to mark Y as finished as well, right? Since X is finished and then Y needs to be finished. So Y will be the next one being finished, all right? And the finish time will be 6, right? Because the time is a global variable, right? After X increments time to 5, then when the Y is the next one being finished, it will increment the time again from 5 to 6. And accordingly, similarly, we'll go back to V, which will mark the finish time for V as 7, which is basically from incrementing from 6 to 7. And then lastly, we will go to the U, which is the vertex U, which has the finish time as 8. Okay, so here is another type of edge marked as forward, right? So it's basically the opposite of the backward, the back edge, because the forward edge will connect from the ancestor to some indirect descendants, right? So that is also some knowledge we will use in the future. Okay. All right, so right now we are done with partially done with the DFS because we start from some vertex U, and then we keep going deep into all the vertices and mark all the discovery time, and then also mark all the finish time during the process that we trace back, right? So one thing we should notice is that, okay, so the vertex that was first discovered actually has the greatest finish time, which means the first discovered vertex is the one being finished at the last. Okay, so that is the characteristic of the DFS, right? Because we go as deep as possible. So when we have traced back to the beginning, it must be the last element, the last vertex being finished. Okay, that is the first half of the algorithm, and we are not done yet because there are some unvisited vertices here. So that will be basically the same execution of the same algorithm, but on the difference on a different part of the graph. Okay, and the left nodes, the left vertices painted in black, we can call it a depth first DFS tree, right? Because it has some root node U, right? And it has all the tree edges from U to V, from V to Y, and Y to X, and also have some non-tree edges like the forward edge and the backward edge. Okay, so that's one tree obtained from the graph. And the next graph, the next tree, right? For example, we will carry on with this procedure. And for example, we will call DFS visit now on the new node, the new vertex W, right? But remember, we will keep the global variable time, right? Since the last time would be 8, so the new discovery time for W would be incremented by 1, which is 9, right? And we need to go through all the adjacency, go through the adjacency list for W, right? Which is, for example, Y and Z. Let's assume that if we go to Y first, but since Y is now black, it's not white, so there will be no recursive call incurred, right? But during this process, we can define a third type of edge, which is marked as C. And the meaning of the C is that it's a cross tree edge, okay, right? Because we actually start from one tree, but connects to a second tree that is already finished, right? So in this case, the algorithm should be able to recognize the should be able to recognize that it's an edge that crosses two trees, right? Basically, the principle is that if I am connecting to a black vertex, right? Then since that black vertex is the one that's already finished, so that's which means it's already visited before the current the vertex W, right? So in that case, the edge will be recognized as the cross edge. Okay, so Y is not the vertex in the current tree, so we will need to go to the next vertex, which is Z, right? And now since Z is white, so it will be visited, and the visit will increment the discovery time to 10. And now since Z has itself has a vertex that's connecting to itself, right? So this edge will also needs to be taken into account as a back edge, right? But that is not our main focus here. And now since Z is done, the time will be incremented by 1, and that will be the finish time for z. And after z is done, we need to go back, right, to the parent, which is w, and the finish time for w would be 11 plus 1, which is 12. Okay, and so far we are done with this second DFS, second round of DFS tree, right? And we have basically go through all the vertices, and that is the results of the DFS, right? So we have a bunch of vertices painted to black, and also all the edges are assigned with meaningful labels. Okay, and let's look at the structure of the results. Right, if we plot all the vertices and the edges as if they were tree nodes, right? Then it's a very typical forest. It's because it's 2 trees. The first tree starts from the U, the vertex U, right? Connects to V, and V to Y, and Y to X. So all the edges here in the bold color, they are the tree edges. Okay, and all the other edges in the dashed type, and also with labels, these are the non-tree edges, but we can classify them as forward, back, or cross nodes. Okay, so it corresponds to the results that we had in the previous slides. Okay, so yeah, so the textbook tells us that the edge types can actually be classified, and the meanings of those labels corresponds to the connection direction, the direction of the edge in the tree or in the graph. So if the edge is connecting from some parent's vertex to the direct child node, direct child vertex, then it's the tree edges because it's part of the tree, right? And if it's it's connecting from the in a reverse order, like from the child, from the descendant to an ancestor, then it's considered as a back, right? It's connecting backward. And the self loops here is considered as a special type of back edges. Okay, and then for the forward, it's the other way around. If I it's connecting from a ancestor to a descendant, but it's not a tree edge. It's a indirect descendant. Then it will be the so-called forward edge. Okay, and the cross edges, actually the meaning is that it's crossing different trees. Okay, so these edges information actually is part of the results, and it is sometimes useful in determining the properties, the structural properties of some of the graphs. Okay, and also we can find a relationship between the color of the two vertices at the two ends of the edge to determine the type of the edge, right? So when we are first explore the edge from U to V, for example, and then we can determine the type of the edge by the color of V. So if V is white, then it's a tree edge, right? That makes sense, right? Because we are exploring the vertex V for the first time, right? And then if V is a gray vertex, which means it's already discovered, right? But it's within the same tree, right? Because it's gray, it's not black, right? And if it's black, then it will be a forward or a cross edge. So that's pretty much for the results we can obtain from the enhanced version for DFS. Right now, actually, for analyzing the running time for DFS, I think we had similar analysis previously, right? So the algorithm is not that difference in terms of the key operations, because essentially it's just a recursive version, recursive DFS algorithm, and the enhancement is just within the some additional attributes like the discovery time and the finish time, and it's just one global variable called time that we use. Okay, so the running time for this enhanced version will not be that different from the recursive or the non-recursive DFS. Okay, so actually there are two parts, right? We have DFS and DFS visits. So on the left, it's just initialization, right? And initialization and actually for loops, right? That go through all the vertices, right? So the range of the for loop is actually determined by this quantity, by the number of vertices. So this part, it will take big theta of v time, and the next analysis is within the DFS visit. Okay, so the DFS visit is actually called exactly once for each vertex. Okay, because it will be only called when that vertex is white, right? If only that vertex is white, it will call the DFS visit, and the same here, right? Within the same within the body of this for loop, only when the color of v is white, it will call the DFS visit. Okay, so and within each call of the vertex for visiting for each vertex, there will be line 4 to 7 that go through all the vertices within the adjacency list. Okay, and the range of this for loop is the length of this adjacency list. Okay, indicated by this quantity. So now here is the same, again, the same problem. It is the length of the adjacency list. Okay, so what is the summation of the length of all the adjacency list? That is the question that we brought up, right, in the previous lecture. Like when the graph is represented by a collection of lists, what is the length of what is the total length of all the adjacency list? So it should be a quantity related to the number of edges, right? So the summation of the total length of all the adjacency lists should be the proportionate to this quantity, right? Depending on the graph, the type of the graph. If it's the directional, it will be different from a undirectional, right? So anyway, we will have two parts for the cost, right? We will have the part for related to the number of vertices, and the cost related to the number of edges. So in total, we will have something that's described by this big theta of v plus e. Okay. So if you remember, that is also the cost for the BFS tree, for the BFS algorithm, right? So in terms of running time, the two algorithms are not that different here. All right, so that is so much for the basic search algorithms for graph. And for the next, starting from the next section, we're gonna look at how the search algorithms can be actually used for the more advanced problems. Okay, the first algorithm, actually the next two algorithms will be dependent on the DFS, and specifically the enhanced version for DFS. Okay, so we'll soon find out why the discovery time and the finish time from returned by the DFS will be useful, and how that will be used. All right, so let's go to the first example. So I think we will have time to cover the first example, which is the algorithm for topological sorts on a graph. And the next will be the strongly connected components that we will cover in the next lecture. Okay, and actually we have introduced these connected components a little bit during the basic data structure review, right? We introduced the disjoint set data structure, right, to represent the connected components in the graph. So we will revisit that part in the next lecture, right? But today we will first talk about topological sorts. Okay. So it's an application of DFS, right? So looking at the definition of it, we need to take this direct acyclic graph, which is known as a DAG, as input. Okay, so it has some constraint. First, it is a directional graph, and more importantly, it is acyclic. Okay, so this acyclic means that there is no cycles in the graph, right? There shouldn't be cycles in the graph. Okay, so if that graph is taken as inputs, then the topological sorts is a linear ordering of all the vertices. So as the name indicates, it's kind of a sorting algorithm, right? It will sort all the vertices in such an order that if the graph contains an edge from U to V, then the U must appear before V in the ordering. Okay, so we want to make the ordering satisfy this condition, right? So if in the ordering we put U before V, oops, that is not a good drawing here. Okay, if we put U before V, right, since the connection is directional, the edge is directional, then that is the correct order, right? So that is correct order. But if we put V here before U, then the edge is pointing from right to left, right? But that is against our direction of sorting the vertices. So this will not be the one. This will not be the correct output. Okay, so basically, these topological sort algorithm is very useful in a lot of situations, a lot of scenarios. Like if we are, for example, if we are using the directed graph to describe the precedence relationship, like the dependencies among all the events, like event A must happen before event B, right? Or we can also think of a graph that describes the package dependency relationship in software engineering. Then we must install package A before install package B, right? Because package B relies on A. So this type of dependency relationships can be described by this direct acyclic graph. And if we are able to output some topological sort that list all the vertices in such an order that the dependency is not violated, right? So that will be very useful in analyzing the dependency relationships between all the vertices. Okay, so the textbook gives such an example, which is the event in terms that how you want to put on all your clothes in the morning, right? So like you want to put on your socks before you put on the shoes, right? So the connection between the socks and shoes is in such a direction, right? It shouldn't be the other way, right? So like the shirt must come before the tie, right? The tie must come before the jacket. The shirt also comes before the belt, right? The belt become before the jacket, and so on. And some vertices, for example, watch is isolated. It doesn't really matter when you put on these events. So given this graph, we want to like sort all the events in an order that they are correctly positioned, so that the one that is relied on must occur before the ones that depends on them. Okay. Okay. So if we look at the results, for example, it can be like this, right? For example, we mix the socks here as the first vertex, right? And the undershort, if undershort appears here, then the pants must be to the right of the undershorts, and the shoes is to the right of all the ones above. So this is a good sorting result, because if you look at the arrows, right, when we put the vertices in such an order along a horizontal line, we can find that all the directed edges, they actually go from left to right. So in this case, we have a correct topological sort output. So that is the result that we want by the definition of topological sorts, right? Because the socks is the sorted as the first event, and all the events afterwards will not violate this ordering, right? All the edges are connecting, pointing from left to right. So how do we achieve this goal, right? We will, as we said before, we will need to utilize the advanced version, the enhanced version for DFS. Okay. So actually, it's quite a simple solution. Okay, if we look at the algorithm, it's just 3 lines of code, but it's a rather abstract description, right? It's not down to the earth implementation, right? But let's just look at the algorithm. First of all, we need to call DFS, right? Which is the enhanced version of DFS that computes the finishing time for each vertex V in the graph, right? And when each vertex is finished, it will insert that vertex to the front of a linked list. Okay, and that means after the DFS is done, all the vertices has been inserted to the linked list, right? Because the algorithm says during the DFS, when each vertex is finished, right, it will be inserted onto the front of a linked list. Okay, so let's look at the some demonstration here, right? So for example, we will first look at the results of the DFS, right? That is the result of the DFS. And remember for example, here we, and also it doesn't require which source vertex to choose. It doesn't really matter. So we can randomly choose the shirt, for example, as the source vertex, right? So the 1 will be the starting time for the discovery time for shirts, and the tie will be the next one, the jackets, right? And the finishing time would be like 4 and 5, right? And then 6, 7, and 8, right? So that would be basically the first tree, and we will have a bunch of trees, but that doesn't really matter. We just need to use the finishing time. So whenever a vertex is finished, it will be inserted to the front. Okay, so in this case, if we just follow this relationship, we'll find that if we start from shirt, the jacket will be the one that will be first finished, right? So jacket will have the smallest finishing time among all the vertices. So it will be inserted to the front of the linked list, all right? And the next one will be the tie, right? Here. And then the belt, right? The belt. And then the shirt, right? And it applies, this principle applies to all the vertices in the graph, and the watch will be the next one, and the shoes, right? So if you look at the finishing time for all the vertices within the final results, they are basically in the descending order for the finish time, right? It ranges from 18, 16, 15, 14, 10, 8, 7, 5, 4, right? So this case will make sure that the edges will not connecting from left to right. Okay, so why this is the case? So if we just think of this problem intuitively, right? So in the tree, in the DFS tree, all the edges are kind of connecting from the parent node to the child node, right? So, and the parent is always finished after the child node is finished, right? The child node will finish first because it's depth first tree. We will go as deep as possible. So the child at the bottom will be the one that's finished first, right? So jacket finished before tie, and tie finished before belt. And because in our algorithm we will insert the vertex that is finished insert to the front of the linked list. So the one that finished earlier will be inserted at the earliest at the beginning of at the head of the linked list. So that will make sure the edges connecting from this later vertex to the beginning to the earlier vertex will always pointing from left to the right. Okay. So I think we will have a second example here. Okay. So here is this is a second example, and I think it's interesting as it also shows that the DFS. Well, I mean, for DFS is not unique, right? Because we can choose different vertices as the source vertex in DFS, and that also means the topological sort is also not unique. Okay, so for example, if this time we don't take shirt as the source vertex, but rather undershorts, right? So the discovery time for undershorts will be 1, right? And then we follow the undershorts to pants, and then belts and the jacket, right? Because this is depth first search, and then 5, 6, 7, 8. So the number to the right of the slash is the finishing time, right? And 9 and 10. Okay, so assume that's true for all the vertices after we are done, right? We'll have a bunch of finishing time. So by the algorithm, by the topological sort algorithm, we will need to this time take the jacket first because it has the earliest finish time. It is finished at 5, right? And then will be the belts, right? And then it will be the shoes, right? Shoes has the 8, right? And then the pants has a finish time 9, and the undershorts 10, socks 12, watch, right? Tie and shirt, right? So that will be the another order for the topological sorts. And if we look at the connections, right? If we look closely at the connections, at the edges, and we'll find that they don't break the principles. It don't violate the requirements that they should connect from left to the right. Okay, so yeah, and also if you think about this, if you like look at these results, and actually you can move around those blocks freely, move around those vertices freely, as long as they don't break the requirements of the topological sort, right? For example, you can move the socks, right, like to the point that's before the shoes but after the pants. That is also okay, right? Because socks doesn't, the socks is not relied on the undershorts or pants, right? And the other vertex of watch is also something that you can move freely, right? As long as they don't break the principles. So you see, depending the results of the topological sort depends on depends on the results of DFS, and the results of DFS also depends on which source you choose, which source vertex you choose. Okay, so the same graph we will have pretty different results depending on the initial conditions. All right. So I think in the last slide, we can analyze the running time for the topological sorts. So because the DFS runs in big zeta of V plus E time, that's something we have analyzed in DFS. And the insert operation on the linked list is also a constant. So the running time for topological is actually no different than a DFS, right? So you can see that DFS has an immediate applications, right? It's a very useful application. So given a graph that is a directional and the acyclic graph, then we can use a DFS on it to determine the dependencies, right? We can we can find we can sort all the vertices in such an order that the ones that is dependent on which always appears before the others, right? So that is a pretty useful package, pretty useful algorithm. Okay. So in analyzing the correctness of the topological sorts, it's actually optional. And I think on the textbook, there's a more detailed explanations. So basically why the topological sorts algorithm works, right? So it basically we need to ask why the enhanced version for DFS will return the correct results of topological sorts. And we will need to use this lemma, okay? So this lemma is like, it says a directed graph G is acyclic if and only if a DFS of G yields no back edges. Yeah, it's optional, right? So we won't be tested on the correctness. So I can probably, yeah, modify these slides to mark the optional requirements to the slide, right? So the lemma, I think this lemma makes sense, right? because if there's a back edge, right? So if we have from jackets points back to pants, then it's correct. It's making some loops, right? Making a cycles where we can go from jacket to pants to belt to jacket again, right? So this is violates the input requirements, right? And the theorem says, right, a topological sort produces a topological. The theorem says that the topological sort procedure that we defined in that way will produce a topological sort of input DAG, right? So you see, this is the algorithm. The capital letter topological sort is the procedure. So actually, the proof says that we just need to show that for any pair of distinct vertices in U and V, if it contains an edge from U to V, then the finish time for V must be smaller than the finish time of U. Okay, so I think that's vertex, that principle is a pretty straightforward property, right? Because in DFS, when you go from U to V, right, because it's depth first search, then the child node or the descendant node will always the one being finished before the U, right? Because after U is visited, we will need to go through the deeper nodes, right? Until all the deeper nodes are finished, then V will be finished. And only after V is finished, the U will be finished, right? So it also says when the edge U to V is explored, then V cannot be gray, because if it's a gray vertex, then that's edge from U to V actually is a back edge, right? And then the back edge actually breaks the previous lemma. We cannot have a back edge, right? And if V is white, then it becomes a descendant of U. So in that case, we will make sure that's for sure, right? The visiting time for V must be smaller than visiting time of F. And in the other case, the same inequality also holds, because if V is black, then it means it's already finished, right? Because we are still exploring from U, then U is not finished yet. So as a result, the finishing time for V is also smaller than finishing time of F. So in either case, the same inequality holds, then which proves the principle proves the assumption that the finishing time for V must be smaller than the finish time of U. Okay, so as long as this holds, this inequality holds, which means for any edge in the graph, we will always have these holds, right? So when we take the nodes, when we take the vertex out, when it's finished, right, we'll make sure that the vertices that has smaller finish time is always on the right, and the one that has a larger finish time is always towards the left, right? Which makes sure that all the edges is always pointing from left to right. Okay, so this is a straightforward proof, and I think it's intuitively it's very reasonable, and I would encourage you to go through the detailed proof in a textbook, and it will help you better understand why how we can utilize the finishing time returned by DFS to conduct such a topological sort algorithm. All right, I think we are done today, and we'll leave the strongly connected component to the next lecture on Thursday. All right.